Hi guys, I'm Arun Agarwal. I'm 6 stars in CodeChef and Master in Code Forces. Welcome to our channel, Learn Competitive Programming with CodeChef. Every week we upload tons of content on competitive programming, so here's a reminder to subscribe and click on the bell icon to stay notified. Today, we're going to discuss a problem named Bash Matrix, which appeared in the February Long Challenge in 2021. This problem is medium hard and has pretty extreme prerequisites. So one of the prerequisites is directed minimum spanning tree, which is a pretty interesting concept. So I'll explain the basic idea of directed minimum spanning tree. But the algorithm you need to know for it is called Edmonds algorithm, and it's fairly advanced. So yeah, you need to get an idea of it beforehand, or you can honestly watch this video even without knowing the algorithm. But to implement it, you need the algorithm. And then a min cost max flow is a very common thing. And yeah, to even understand this video, you'll probably need know min cost max flow beforehand. So let's look at the problem statement. The problem states a Bash matrix is a matrix with n rows numbered from 1 through n and n columns numbered again from 1 through n. So it's an n by n matrix. Now, basically, each element in the matrix has um, a character either U, D, L, or R. Okay. Now, U, D, L, or R denotes a direction for that cell. So if if the character in the cell RC is R, then you move up to the cell R and C plus 1. I'm sorry, move up, no, you move right to the cell RC plus 1. If it's left, then you move left to the cell RC minus 1. If it's U, you move to R minus 1C, which is up, and if it's D, you move down to R plus 1C. In addition, by these instructions, it should be impossible to leave the matrix. Okay. Now, once in his childhood, Chef had chosen a Bash matrix, and for each cell RC of the matrix, he did the following thing. He marked all cells as not visited, started in cell RC, and while he has not previously visited the cell he is currently in, move in the matrix following the instruction. He stops moving as soon as he finds out that he's in a cell that he has visited before. So basically what we have here is the matrix can be visualized as kind of a graph where each node has may have large in degree but has out degree 1, and you keep on moving along the outward edges from the starting node until you encounter the node you've already visited. Okay. Now he notes down the cell at which he stops. Okay. And so for cell RC, you have a cell XY where so XY is the first repeated cell from RC. Okay. And since every node has an out degree, you can show that there'll always be a cycle no matter where you start. Okay, cool. So the problem is that we're given this matrix where for each cell you're given where the place at which we stop, and we have to reconstruct. Do we have to reconstruct? Uh, okay, yeah. So we do have to reconstruct the matrix which would satisfy these properties. Furthermore, for each direction, ULDR, you're basically given a cost PU, PL, PD, and PR respectively, and you have to construct a matrix such that the total cost is minimized. That means that for each U, L, D, and R you add in the matrix, the sum of PU multiplied by the amount you add, PL multiplied by the amount you add, PD multiplied by the amount of you add, and PR multiplied by the amount you add is minimized, right? So that's what minimizing the cost means. Okay, cool. So yeah, our constraints are n is less than equal to 50, PUPL PDPR is less than equal to 10 to the power 5, and yeah, XY is less than equal to n. So basically, so an important thing to note is that it's possible that there is no answer. Okay, that's a possibility. It's not guaranteed that there's an answer. Otherwise, we print n plus 1 lines. The first line contains a single integer, which is the cost, and then we print the matrix that we generate. Okay, cool. So this problem is actually very intricate. So rather than giving like a complete walkthrough of the algorithm step by step, I'll give you guys a very good way to approach the problem, and I'll write down the key steps, and I'll leave it to you guys to focus on the implementation challenges. Okay, cool. Because the implementations are huge, so it's just not feasible for a video. Yep. Okay. So let's go through an example case. I think we should do. Yeah. Okay. So this is actually a rather big example. So okay. Yeah. Let's look at this case. Okay. Or rather, let's look at this case. So we're given a matrix as input, which is 1 1 1 2 2 3 2 1 2 2 2 3 3 1 3 2 and 3 3. Okay. Okay. So basically what this means is that if you start at cell 1 1 and you keep on going along the general edges, then you'll end up at 1 1 only again. Okay, that'll be the first cell you revisit. Similarly, if you start 1 2, you'll end at 1 2 again. If you're at 2 1, you'll end at 2 1 again, 2 2 again, same thing. Then 2 3 also. So if you start at 1 3, then you'll end up at 2 3. That'll be the first cell you revisit. And if you start at 2 3, then 2 3 again will be the first cell you revisit. Then similarly 3 3, if you start 3 3, 3 3 will be the first cell you revisit. If you start 3 2, 3 2 will be the first cell you revisit. If you start 3 1, 3 1 will be the first cell you revisit. Okay. So a matrix which I can try to construct is basically something like an edge from here to here, from here to here, here to here, 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 and we have one edge going downward here. So basically this manifests itself in the form R D D R D D, then this has up, this has right, this has down, this has left, this has left, this has up. Okay, and we can verify this is true. So let's choose something. So I'll show you for let's say for 2 2 for example. So you have R which goes to 2 3, down 3 3, left 3 2, left 3 1, up 2 1, up 1 1, right 1 2, and then down again to 2 2. And so 2 2 is revisited, therefore 2 2 it is. Okay. And so all of these actually map to themselves only. The only one that revisits a different node the first time is 2 3, which 1 3, sorry, which actually revisits 2 3 for the first time. So we can see over here if we start 1 3, we go down here, then we keep following this path all the way around, and we eventually come back down again to 2 3 only. Okay, cool. Uh, yeah, so let's see what they had given, and yeah, okay. So if you see, they've actually given a different solution, right? They've given some RLD, DLL, RRU, RL, yeah, okay. So yeah, they've given a different solution, okay? They've done so, and just based on this, actually, I can give you a different solution right now as well. So I've given one possible direction set already. let me give another one. Okay, so let's erase everything. Not everything. Let's just erase the direction of the edges and propose an alternate solution. Okay, and this kind of alternate solution will help you look at a problem later. Okay, so yeah, let's say we do these two. We do maybe this and this. We have this and this and this, right? And if you see, this is actually valid. If you start 1 1, you go to 1 2 and come back to 1 1, so 1 1 will be revisited. If you start 1 2, you go to 1 1, come back to 1 2, again 1 2. Similarly, it's the same thing for all these pairs. If you start 2 3, if you start 1 3, you go to 2 3, you go to 3 3, then you come back up to 2 3, so 2 3 will be first thing revisited, right? So this is also completely valid, okay? And if you see the left, right, up, down frequency is actually different in this one, right? So the cost is also different. So yeah, that's the challenge we have. And one of the conditions that was given is that we should never be able to leave the matrix, but that's not really something that we have to keep in mind, right? Like as long as we do something very reasonable, we'll never end up leaving the matrix, right? Because like it just doesn't make sense. If we fulfilled this condition of this, if in our solution we fulfill the condition of this matrix being satisfied, then it's just not possible to do if we leave the matrix at any point, right? So yeah, that I mean, they just written that to be very clear, but it's not something that we have to worry too much about while building it. Okay, cool. So now let's think about how we want to approach this. So the first thing that we should notice is that nodes. So for all ij, where so let me see what this input matrix is called in the so it's called X. Okay. So for all ij, where xij is equal to ij, okay, basically meaning that the final position of the node is the node itself. So 1 1 ends at 1 1, as opposed to like 2 1 3 which ends at 2 3, right? So I'm referring to all of these nodes which end it themselves. So let's call these um, terminal nodes. Okay. Now terminal nodes clearly are nodes which are involved in a cycle, right? Meaning that they are nodes which are per se some involved in cycles. If you see this 1 1, let's say this is 1 1, and this 1 2, these nodes are in the middle of the cycle, right? Meaning that there's some chain of nodes starting at it and ending at it. Okay. If you see 1 3, however, 1 3 connects to 2 3, which connects to 3 3. And note that if there was a cycle, obviously between C3 and 1C there cannot be, but if there was some convoluted way in which there's a cycle, then eventually it would have to end up at 1C only, right? So therefore, it's easy to see that these are equivalent, right? I'm not going to go into a proof for it, but like it's very obvious to see, right? And yeah, you can see that 2 3 ended itself. So actually, there's the edge from 3 3 to 2 3, right? Right. So you can see 2 3 and 3 3 are both self-contained in a cycle. However, 1 3 is kind of like an external edge into the cycle, right? Yeah. So these black are the terminal nodes, and this one is like, let's call it a non-terminal node, really, just to avoid too much extra notation. Okay. Now, 1 second. Okay. Cool. So, yeah. Now, what do we do with terminal nodes? Well, we know that terminal nodes are involved in a cycle, which means that there's a chain of nodes starting from it and ending at it, right? Now, note that any cycle, uh, for any cycle, the number of down edges has to be equal to the number of up edges, right? Because you have to eventually come back to, so let's say starting at xy, down makes xy turn into x plus 1y, and up makes xy turn into, let's say, x minus 1y, right? Oh, did I make it x plus y? I'm sorry. I don't know what I wrote there. It's x plus 1y. Yeah. Okay. So if and R and L have no effect on x, they only act on y. So if eventually this chain has to come back to x, then the u and d need to cancel each other out, right? So that's why d is equal to u. Similarly, R, oh, this is an arrow, by the way. This is not really like minus sign. Yeah. So R is equal to left. Okay. So total number of edges and therefore the total number of nodes in the cycle is equal to 2d plus 2r. Okay, is equal to 2 into d plus r. So d plus r itself is not really relevant. The more important thing is that this is always even. Means that let's say we forget about all these non-terminal nodes, okay, and we include only the terminal nodes in the graph, then this graph will only contain even left cycles. And this brings up a very important property, which is the graph of only terminal nodes is bipartite. Okay. So bipartite basically means that we can divide all the nodes into two sets, okay, such that uh, there are no edges between two nodes in the same set, right? So there are only edges going across. So like one cycle would look something like, and let me just highlight the cycle node in different cycle edge in a different color. It looks like something like this, right? And we can just add direction if you want. So yeah, right? Cool. And yeah, there can be multiple cycles overlapping. Overlapping as in not connected to the same node, but there can be multiple cycles in the overall graph, obviously. Okay. Now, one important observation is that uh, it's optimal for all cycles to have length less than equal to 2. Okay. The proof again I will leave as an exercise, but I'm thinking about leaving an exercise. Like you really shouldn't bother with the proof, but the intuition that you should have is basically that if you have like some complex graph like this, then you're kind of wasting your time with a lot of these. I mean, you're not really wasting your time with the edges. It's just that you can make this a lot simpler graph. Like instead of having such a complicated thing, you can just do. Let me erase this. So just remember the nodes involved. Okay. So this node, this node, this node, and this node should each be in some cycle, and they don't necessarily have to. The cycle doesn't have to contain all of them, right? All that matters is that they all have to be in one cycle. Okay. So instead of doing this complicated stuff, why don't we just keep keep cycles like this, right? You can show that like the up down right left costing doesn't really change at all. Okay. Like uh, just that this is always simpler, right? Cool. Um, yeah, so now that we've shown that there's always a way to do it in a bipart, in like a lens to cycle way, then this gives an interesting way for us to be able to solve for the directions of all of the terminal nodes very, very easily. And this is using minimum cost maximum bipartite matching. Okay, and this is basically minimum cost max flow only. Like if you've done max flow, then you should really know that bipartite matching is just like a max flow case only with all the flows set as one. Okay, the way to do this would be is that okay, so there's kind of one okay, so I'll just show this to you guys. So note that any thing in ij, any cell ij can be connected to either ij plus 1, ij minus 1, I plus 1 j, or I minus 1 j. Either case, note that ij modulo 2 is not equal to the like what do you want to call it? Let's call this xy. So it's not equal to I'm sorry, I plus j modulo 2 is not equal to x plus y modulo 2, right? And this is like pretty obvious, right? Because we add 1 to it wherever we go. So obviously the modulo changes. If it was 0 becomes 1, if it was 1 becomes 0, right? So in our bipartite graph, what we can do is we can have all of the sort of the even edges nodes on one side and the odd on edges on the other side. Okay, even are those edges such that I plus j mod 2 is equal to 0, and odd are ones for which this is not true. Okay, cool. Yeah, so that's a division of bipartite like into bipartite graph. So now what we do is like if we want to create so I'm assuming you guys are familiar with the basic idea of bipartite matching. So we basically have like I'll tell you the idea. Okay, so the way to make a flow network out of this is we have like some sink. Okay, we have our even terminal nodes, we have our odd terminal nodes. Okay, let's just say that they have the same they are the same number, and I mean if they aren't the same number, then this is like not possible. So it would be a minus one if they don't. Okay, so the idea is we do this connection here. Okay, okay, now this green thing here is the source, and this red thing here is the sink. Okay, and then the capacity of each of these is set to 1. Okay, similarly the capacity of all of these is set to 1, and so whichever nodes are adjacent, right? So adjacent basically means that like ij is adjacent to all of the, so adjacent means that for example this node is adjacent to these 4 nodes, basically nodes that it can have a direct edge with. Okay, so then we make an edge with all of the adjacent nodes. Okay, so let's say this is adjacent, this will not necessarily satisfy any kind of grid, by the way. I'm just showing it to you. For example, let's say this is adjacent only this is adjacent of this, and this is adjacent of this. Okay, so now let's say that this is a like a row connection, meaning that like let's say this is cell ij. Okay, and this is cell like ij plus 1, okay, or j minus 1, same thing. So then the cost of creating an edge from ij to ij plus 1 and then from ij plus 1 to ij is basically r plus l, right? And similarly, let's say that this one down here is actually a column connection. So basically column connection means that, so to give you an idea, the row connection basically means that they're in the same row, right? They're connected in the same row. So basically 2 2 is connected to 2 3 in the same row, and 2 2 is connected to 2 1 in the same row. So that's a row connection. And a column connection is basically something like this, okay? Like, yeah, so 2 2 is connected to 1 2 in a column and 2 2 is connected to 3 2 in a column, okay? So now, for a column connection, actually the cost should be U plus D. Uh, Sorry, yeah, the cost should be U plus D, okay? So you do this for everything, okay? And obviously you set the flow capacity for each thing to 1 only. These things that I'm telling you right now are the costs, okay? The R plus L and U plus D and stuff. And then you do max flow min cost thing, okay? You get the maximum for the minimum cost. Now, if the uh, max flow is not equal to the number of terminal nodes divided by 2, then output minus 1. Okay, simple as that. Like, if you can't connect all the terminal nodes in a cycle somehow, then you like the input graph is invalid and and the answer is not possible. Okay, so that's the one major part of problem done. Okay, we are done dealing with terminal nodes. So now what we have to deal with are non-terminal nodes. Now, the way non-terminal nodes work is, so let's say now I'm gonna temporarily or maybe permanently leave the grid structure and work on general graphs. Okay, so let's say this red thing is a terminal node. Okay, and all of these green things, okay, all of these green things somehow end up on red. Okay, meaning that they take like some series of nodes, but the first node that's revisited is red. Okay, now a few properties are that these green nodes must be connected to red only via a direct sequence of green nodes, which are also which also want to end up on red only. Okay, so basically what I'm saying is that red is a terminal node ij. Okay, now we described the concept of edges between these cells, right? So I'm saying that if there's some xy which is green, meaning that it wants to end up at ij, the first revisited node in the path should be ij, then it should be connected to red via a bunch of nodes. Like doesn't really matter, and all of these nodes should be non-terminal, and each of these nodes should also end up at ij. Okay, and the proof is again trivial. This does not mean that there cannot be another path with some other random nodes. Okay, this just means, so this is also fine, but this just means that there must exist a path with the good nodes, the non-terminal nodes which end up at ij. Okay, now we want to find, like, using these green nodes only, we want to find a way to connect all of these. Okay, so the algorithm we're going to use here is uh, directed minimum spanning tree. Sorry for that. Okay. So what is the minimum directed minimum spanning tree? Okay. So let's say you have a directed graph. Okay, and which is built upon the node V edges E, and each edge has a cost. Let's call that W. Okay. Now, a directed minimum spanning tree is a subset of V and a subset of E, okay, basically such that um, the subgraph formed, the subgraph when like without direction, okay, like if you make the subgraph an undirected graph, okay, then it's a tree. Okay, the subgraph without direction is a tree, and from the root of the tree. So basically, this is a rooted tree. Okay, a directed minimum spanning tree is always built with respect to a root. Okay, so uh, the subgraph without direction is a tree, and there always exists a path from the root to every node in the tree. And I actually apologize because I think I made a mistake while defining this. So it's basically a subset of V, but the directed minimum spanning tree actually has to contain all of V. Okay, so it's not a subset of V. It contains the entire original node set, the vertex set, and it contains a subset of the edge set. Okay, without direction is a tree, and um, yeah, there's a path from the root to every node in tree, and this is with direction. So what this basically means is that our directed minimum span tree looks something like, okay, it looks like a regular tree only. Let's say, uh, you know, uh, yeah. So you have like a regular tree, okay, and all of the edges are like kind of downwards, okay. So this is built with respect to a very specific root, and all of the edges are downwards, okay. You get what I'm saying, right? So with the root, you can reach anything, but that's it. Like the root is the only node from which you can reach everything. Okay, and the like minimum, I guess, stands for itself, but the idea is that each edge has a cost with it. Each edge has a cost, and so the sum of edge cost, actually, I should have wrote cost of edge really, but the sum of the edge costs are minimum. So you have to select the subset of edges so that the total cost is a minimum and it satisfies this property. Now, how do I use this? Well, I'm sure a lot of you probably actually have the idea by now, but the way you use this is basically you set, so you do this for all terminal nodes, okay? You set ij as basically the head of the tree, okay? And so you set this as the root. And now, remember we said that for all like non-terminal nodes which end at ij being terminal, then there must be a path consisting of non-terminal nodes ending at ij. Okay. So what this basically means is we build a graph out of only these. Uh, yeah, we built a graph out of only these green nodes. Okay. So yeah, let's say we built some graph out of these green nodes. Okay. Um, and actually, so what we actually want is for all of the green nodes to be able to reach the root, right? So actually, everything would be directed upwards towards the root, okay? But just that we can use the directed minimum spanning tree algorithm for our like easiness sake, we direct the edges in the opposite direction, okay? But we give cost like as we would in the graph. So, for example, if this is ij and this is, let's say, I plus 1j. So this is actually uh, this is actually an edge from I plus 1j to ij, right? So this is actually an edge in the let's say where I plus 1j to ij. So this is an edge going up, right? So for this we would actually add p of u, but for convenience we would direct this downwards away from the root. Okay, this is just that our algorithm can work. And so this, while we are actually making a downwards edge, we add pu only. Okay, cool. So the idea is that we make this entire graph. Okay, and now immediately you can see that if in this graph with respect to a terminal node ij, If there is a single node in this graph which is not reachable from ij, then the entire matrix that we've been given as input is invalid. So in that case, our output would be -1. Okay. However, if every node is reachable, then it must have a directed minimum spanning tree, and so we will find this directed minimum spanning tree. Okay. And to do this is pretty simple using Edmonds algorithm. So Edmonds algorithm itself, I'm not going to be explaining. Okay, it's like really the algorithm itself is very complicated. It's a direct this problem uses the algorithm directly, so I said it's simple, but the algorithm itself is very complicated. Okay, so good luck. You should check out the Wikipedia page. That was the uh, most that had the best explanation in my opinion. Okay, and yeah, the author solution stuff I'll probably put in the comments. You can check it out. Again, just for the complexity of both uh, Minkow's Maxwell and Edmonds algo, like I'm not going to explain the code in the video, but yeah, it'll be in the comment section, so you can go check it out. And if you understand the process very well, then honestly, even better than seeing the author's code is just to code it yourself, because like like I can tell you from experience, trying to understand somebody else's code for this problem is way harder than just doing it yourself. Okay. Yeah. So yeah, this is so we just directly use Edmonds algorithm here, and using that we get an idea of which edges we should maintain, okay, and which edges can be something else, doesn't matter, okay. Like something else actually means that they won't exist at all, not that they can be directed in some other way or anything, okay. Yeah. So just to reiterate, if we do this for every ij which is the terminal node, then we're done. Okay, because we've handled terminal and non-terminal nodes. Okay, so just to reiterate, this is what we've done. The first thing is we created a bipartite graph between the set of nodes ij such that uh, such that I plus j mod 2 is equal to 0, and the set of nodes such that uh, I plus j mod 2 is equal to 1. Okay. Now, to we added edges in the bipartite graph between adjacent grid cells. Okay. And if it was the row connection, which I mentioned earlier, like basically they're in the same row, then the cost was left plus right. If they're in the same column, then the cost was up plus down. Okay. 3, we used min cost max flow to get a minimum cost bipartite matching on this graph. Okay. And we got the cost plus config. Config basically means the configuration, meaning like LUD, whatever you assign to each node, that's the configuration. Okay. Cost plus config for terminal nodes. Then for non-terminal nodes, so we iterate over all ij such that ij is terminal. Now, inside this, what do we do? Let me use a different color. One, we construct a graph with opposite direction but correct cost. Sorry, between all non-terminal nodes ending at ij and ij itself. Then to basically we will run Edmund's algorithm on this. With uh, ij as the root of the tree, and then see we get cost and config for all nodes ending at ij. So yeah, it's really quite a beautiful problem. It's difficult to implement, but the problem itself is quite beautiful. Yeah. So we have it for terminal nodes, we have it for non-terminal nodes. So all we do is output. Yeah. So this is a pretty good guide which will help you write the code. Okay. Cool. Um